So now that's good. We know how to solve the linear relaxation for our root problem, okay, for our original problem. That's a fractional solution, and that gives us an objective value, 9.8. So you may double check by yourself. And then once we do that, we know, okay, there is a fractional value. That fractional value obviously is within 0 and 1. So we add two constraints. x2 is less than or equal to 0, or x2 is greater than or equal to 1. So let's talk about the first problem. Here, we're going to add a constraint saying that x2 is less than or equal to 0 into our formulation. So what does that mean? That means in any case, when you are doing this, your x2 has no other option. x2 must be 0 for sure. So this is fixed when you try to solve this problem. So you still have 4 variables, 4 items to choose from. Then how to do that? Well, again, that's a continuous knapsack problem. You will still do the ratio and then still do the sorting. Item 3 will still be sorted as the first one, item 4 the second one, item 5 the third one, and item 1 the last one. So you will repeat the process that pretty much you already did. So you're going to take 100% of item 3, 100% of item 4, 100% of item 5. After that, you still have 3 kilograms, and you see that for item 1, taking all of them requires 4 kilograms. So that means here you may only take 3 over 4. And that means 75% of item 1. So that's how you solve the second problem. Okay, you first fix the value for x2 as 0, and then use the same sorting idea to deal with the remaining 4 items. This gives you another solution. Which gives you 9.5. Again, it's not integer, so we may need to branch further. We also want to take a look at the other subproblem. So here we have a constraint saying that your x2 must be 1. So in that case, what does that mean? Your x2 must be 1. You have no other choice. And once you say your x2 must be 1, that's going to consume a few items. That's going to consume a few capacity for your particular knapsack. Okay, you probably still remember that your item 2 takes 5 kilograms. Okay, so if your item 2 takes 5 kilograms and in total you have 11 kilograms, then that means here you already used 5, so you still have 6 kilograms as your knapsack capacity. You're going to ask yourself, what's the best way to choose among the remaining 4 items when you only have 6 kilograms? So you're going to take the whole item 2, item 3, the whole item 4, and now when you are talking about item 5, you already run out of capacity. So for item 5, you only take 1/2 of it. And then there's no way for you to take item 1. So that's how you get this particular solution. And it happens that this solution, unfortunately, is also fractional. So you see that there is a fractional value for x5. So that means we somehow may need to further do some branch and bound on this one. So here, given that x1 is fractional, we may say x1 is less than or equal to 0 and x1 is greater than or equal to 1. So then for this particular subproblem, now we have 2 variables fixed. x1 must be 0 and x2 also must be 0. So you probably may convince yourself that then you have 11 kilograms to serve the last 3 items. You're going to take all of them because you have the capacity to do that. That's going to be an integer solution, and that's your first candidate solution. So that's good. And also, if you move on to your next subproblem here, you're going to fix yourself saying that x1 must be 1, x2 must be 0. In that case, again, you have some residual capacity, and you try to take all of them, all of item 3, all of item 4, and then after that, you only have 3 kilograms on hand. So you're going to take 3/4 for item 5. Okay, so once you do that, you will get this particular solution where you still have a fractional value, and this objective value 9.25 seems to be hopeful. If we keep branching, maybe it may still generate a solution that is better than the candidate solution currently, which is the solution for x4. So that's the current situation. So I guess you would now conclude one thing. Whenever you are using branch and bound to solve knapsack, for any node, you first fix some values and then use residual capacity to deal with the remaining items. And that's again another continuous knapsack problem, and that's how you may solve everything. So let's say we now take a look at the values, and we agree that 9.5 seems to be a better choice. So let's say we first branch on 9.5. And then here, we're going to say your x5 is not good. So we're going to say x5 should be less than or equal to 0 or greater than or equal to 1. Once we do that, very quickly, we may get another fractional solution, and each of them gives us some kind of objective values. So up to here, we are having this one, and this one. We are having 3 solutions. All these 3 solutions are fractional. So maybe we may think about whether we want to keep branching on them or not. 9.25 is larger than 3 and then larger than 8. So ideally, this should be a candidate that we should keep branching on it. 9 is greater than 8, so we should take this as a candidate. 26/3. If you do some quick calculation, you're going to get 8 point something. Okay, so somehow 8 point something seems to be greater than 8. So if you think in that way, you may say, okay, this is still hopeful. But don't forget that for this particular problem, because your values of variables can only be integers, and your objective function have all the coefficients that are integers. So that means if you are going to branch on this, there's no way for you to get an integer solution which gives you a z value that is greater than 8. It's impossible. The maximum possible integer value that you may get along this particular direction is just 8. And there's no hope to be better than the current one. So if you think in that way, there's no need to branch on this because of all those integer variable, integer objective coefficient idea. So you may do this or you may choose not to do this, because if you may have fractional variables or fractional coefficients, then the previous discussion does not work. But in this particular case, you may choose whatever you want. You may do this or choose not to do this. Okay? So let's say we keep doing this way. So we take a look at 9.25 and try to branch on x5. Once we do that, first we get a solution, and our solution here, 10110, gives us 7. Another solution, which says your x2 should be 0, x1 should be 1, x5 should be 1, gives us 10101. This gives us 9 as your objective value. Then immediately this solution 10101, this solution dominates the original candidate solution. So this one becomes the new optimal solution, new current optimal solution. Then we are lucky because there's no need to keep branching on subproblem 6. Why is that? Because in this case, this guy cannot generate any integer solution that is better than the current solution. So there's no need to do this. And of course, there's also no need to do the subproblem 7. So x9 is optimal, and then we are done with this knapsack problem. So a quick remark is that the major process, again, is still branch and bound. The only thing that is unique is that we have a special way to solve the linear relaxation of the knapsack problem. So for knapsack problem is this way. For some other kind of problems, we also face the same situations. It happens that some cases when you are solving an integer program, you need to work on its linear relaxation. If that linear program for that linear relaxation have some special properties, then we may customize the process for solving each node. Somehow that means we may customize the whole branch and bound algorithm. That's possible. That's always possible. And that's something that in some sense may be encouraged. If you really want to use branch and bound to solve a problem, it may take a lot of time, right? So saving some time for each node can be a good idea. That's also a lot, in many cases, some researchers are trying to do, trying to see some special properties for each linear relaxation through branch and bound. That may also be a way to speed it up, and that's be a way to make branch and bound a more realistic, more practical algorithm that may be applied in practice.